So if you're watching these videos in order and you've just finished the video about operations of functions, we had been talking about the idea of composition and decomposition. And so we want to kind of take that idea, that theme of being able to undo stuff and expand on it. We've mentioned the idea, like realistically, you write something, you can erase it. And mathematically, you've got stuff that you multiplied, you can do some division and undo the multiplication. So if we talk about one function by itself, is there another function that can undo the effects? So you can kind of think of these functions as, are they half of a circle? So can I start with a number, apply a function f, take that new number, apply some new second function that will always return me to that original value? But that has to work in both directions, because again, we would want things to be as versatile and useful as possible. So if we started with the number that we had down here at the bottom and we applied that second function first and the first function next, do we get back around that circle? So it's got to work with both of those kinds of orderings, like one function and then the other one function and then the other one. It's got to work in both of those ways. So if there is something like that, cool, that function, we can undo the effects of it. It would be what we call invertible. Now, as it turns out, only certain kinds of functions are invertible, and those are referred to as one-to-one. So there's got to be this one-to-one correspondence, x value, y value. There's got to be a one-to-one correspondence that goes in both directions. So one x value goes to one y value. Well, you know what? That had to happen, all right? Part of what we've got with functions, we've got an x value going to one y value. An x value cannot go to two different y values. So that's already taken care of because we are already dealing with functions. But it's got to go the other way. Y value, one y value going to one x value. It's got to go that direction too. So that now means y values coming from only one x value. That's an extra little something special that we've got happening. Now, when we have that happening, that inverse function, we're going to use some special notation for it. We're going to use a superscript. It's not a power, not a power. It's a superscript. So this is translated, so our shorthand, right? Our shorthand, our quartz stenographer style, F inverse. That's what that is saying in words. F inverse, not F with a power, not a power. That's a superscript that is referring to that inverse function. So F inverse of x. So again, the way that this works, start with a number, apply your f function, get a new number, take that, plug it into your inverse, you end up where you started. But we've got to be able to use that inverse function first also. So if we take the correct kind of number, plug it into our inverse function, get back a number, take that, plug it into our original function f, we end up where we started. So again, there's that full circle kind of idea. It doesn't matter where on the circle we start. It doesn't matter which function we apply first. We've got to start somewhere and end up right back there again. And it's got to be no matter what we start with, that as long as it's allowed. And it's got to be no matter which function we use first, whether it's the original function f or if it's the inverse function. So it's got to all work in that sort of way. Because of all of this, here's what's got to be going on. instead of a vertical line test, which already got us to having functions, this extra condition about being one-to-one means that we have what we would call a horizontal line test. So this is going to tell us whether we've got one-to-one, and as soon as we've got one-to-one, that automatically means that there is an inverse function. Have to worry about finding that in a hot minute, but there at least is one anytime we have a function that is one-to-one. So the horizontal line test is just a modification of the vertical line test. Any place that they mention vertical, we're going to change it to horizontal, and then we're good to go. If every horizontal line crosses a function no more than once, then the function is one-to-one. Cool. Oh, snap. Not one-to-one. So, well, hey, there's one of our real basic functions right there. Quadratic function, not one-to-one. Square root function, that is one-to-one. Vertical line hits once. Vertical line down here hits no times. Vertical line hits once. Vertical line hits once. Vertical line hits once. Far enough out that way. That's all good. That's going to be one-to-one. That's going to be one-to-one. That's got an inverse. That does not. So how about finding an inverse? Well, as it turns out, that's a pretty cool sort of idea that's wrapped up in the business of composition, and it does thankfully only use some of our basic algebra skills. Let's take a look at this. We keep this as a really mild example here. Let's start with this function, f of x equals 2x minus 1, and let's find this inverse function. Now, Ms. Brown, how do we know it's got it? If we took that sucker and graphed it, we would get a line. If we checked out that line based on this horizontal line test, hits once, hits once, hits once, hits once, hits once, hits once. All of our horizontal lines are going to hit this graph only one time. That's one-to-one. It's got an inverse. So now it's our job to follow these steps. Ooh, 4 of them. That's not bad. Follow those 4 steps and find that inverse function. So we start out with our original function. The first step, very cosmetic. Let's, for the sake of the work that we have to do, replace that function notation, f of x, with a y. So just one symbol, real nice and simple to keep track of. Let's just use a y. Step 2 also happens to be just very cosmetic. Interchange the x's and y's. Anywhere you see a y, write an x. Anywhere you see an x, write a y. That's super direct to take care of. Step 3, solve. Oh, well, there's some algebra skills coming into play. That's not cosmetic at all. Solve for y. So here's where we actually have that work to complete, where we've got to solve for y. Well, if we've got to solve for y, we're going to add 1 on both sides. We're going to then divide by 2 on both sides. That gets us the y equals. Cool. Step 4, hey, that's a cosmetic as well. Now, let's replace the y with f inverse. So we did a little equation solving, and boom, like all the rest of this stuff was just super cosmetic. Yeah, as long as we can solve equations, and we've got plenty of experience with it at this stage, as long as we can solve equations, we can do this. So the y equals, instead of the f of x equals, cosmetic. Anywhere we see a y, replace it with an x. Anywhere we see an x, replace it with a y. Boom. Little xy switcheroo, purely cosmetic. Little equation solving. This one, again, we kept more simple, more direct. So solve for y. And then again, that very last step, that cosmetic element of instead of the y, use your function notation. Our original function was f, so f inverse of x is equal to x plus 1 all over 2. There's our inverse function. How do we know? What if we made a mistake? Well, remember that we've got that underpinning as composition. We've got that full circle kind of aspect going on. So there is a set of compositions that we could do in order to work through that. We'll talk about that in a moment. Let's try to keep the list of steps up for as long as we can and go through a second example here. So replace the function notation with a y. So here we have a new function. This one's h of x. H of x is equal to the square root of x minus 2 plus 9. We want to find the inverse of that. Well, how do we know it's got an inverse? They're telling us to find the inverse. In a case like this, they're not going to try to pull a fast one and tell you to find something that isn't there. They're not going to send you on a wild goose chase. So, the fact that they're asking you to find an inverse function means that there is something to find. That's one thing. But for anybody that's very skeptical, you can graph that sucker. Well, let's do this first step real quick, because that's the kind of thing that we would actually see if we were going to go into our graphing calculator. So y equals, instead of the function notation, we would go and type this in to the calculator, the graphing calculator. So we go into our graphing menu. In the y equals, we type in our square root, parentheses x minus 2, close parentheses. To end the square root, type in the plus 9 at the tail end, hit the graph button, and what's going to be happening? Well, I already showed you there's that little curve earlier from our horizontal line test. And that curve, in this particular case, is going to start at x equals 2. And when x is equal to 2, y is equal to 9. And so that, coming from that graph, what we're seeing of that curve that's shaped like that, I'm doing the hand motion, shaped like that hand motion there, starts at x equals 2, y equals 9, and goes upward. So x is greater than or equal to 2. The y is greater than or equal to 9. Based on that shape, all of the horizontal line test is shaping up just fine. So if you're feeling really skeptical and graph that for yourself, you can verify that it passes the horizontal line test. H of x is 1 to 1. H of x has an inverse. The second step that we need to do is to interchange the y and the x. An x and y switcheroo, if you will. Instead of a y, we're going to write an x. All the other symbols are going to stay the same, except, instead of the x, we're going to write a y. So how's that going to look? Well, that's going to be an x equals square root of a y minus 2 plus 9 at the end. As soon as we've switched out the x and the y's, this side note that we've made is going to change as well. Instead of x greater than or equal to 2, that's now going to be switched out and say y is greater than or equal to 2. Instead of y greater than or equal to 9, it's now going to say that that part of the note is x is greater than or equal to 9. This, in fact, may be helpful for us to have. Not only is it helping us practice our graphing skills at the very beginning and our testing skills for making sure that we've got a one-to-one function that is also therefore invertible, but this is also going to help us if they ask us later on to plug in some stuff. We need to know that the only stuff we're allowed to plug in is greater than or equal to 9. We wouldn't be allowed to plug in something like -4 for x. It's not allowed. Solve for y. So now we got to bring in our algebra stuff. Our algebra stuff, I got a square root showing up. So that means I got to get that square root by itself. Going to have to subtract 9 on both sides. Got to get rid of the square root. A squared gets rid of the square root. So I'm going to have to square both sides. Still got to solve for y. One last thing to do. Got to add 2 on both sides to get the y completely and totally by itself. And our last step. We don't want to forget about our last step. We've got to be clear in communicating. We found the inverse function for h of x. We found h inverse of x. We got to spell it out real clearly. The inverse. So we'll just throw that here with our correct notation. Our inverse function, h inverse of x, is equal to that parentheses x minus 9 parentheses squared plus 2. And now you maybe think back, well, wait a minute, Mr. Brown, you told us in that earlier example there was that quadratic graph that you gave us, and that sucker didn't have an inverse. But now there's this quadratic function. What? And it has to do with those side notes that we made. Specifically, it has to do with this x is greater than or equal to 9. That note is still in effect. If that note is still in effect, if we take our graphing calculator, graph this function, this h inverse function, the only part of that graph that we would want to pay attention to is the part where x is greater than or equal to 9. So what we know about those quadratic functions, that x is equal to 9, that's our axis of symmetry. And that means that the part of what we care about from the graphing calculator is only going to be that right-hand half of the parabola. It's not going to be the left hand, because x is greater than or equal to 9. So there's some sneaky little things that are going on here interacting with one another, and we want to make sure that we're aware of them. Making these little side notes helps us make sure that we are aware of those so that we're not getting ourselves confused about things. But again, let's really try to hammer home that idea with just a quick little evaluation set of comments. If we want to evaluate our inverse function for x is equal to 10, 10 is greater than or equal to 9, that's allowed. We are perfectly fine with plugging in the 10 and getting a value of 3. Okay, now evaluate the function for x equals 0. 0 greater than or equal to 9. No, it's not. We're not allowed to do that. We're not allowed to do that in the sense of that's not allowed in this particular case because there's this restriction. Our function is only good for when x is greater than or equal to 9. So it doesn't matter that, like, mechanically, can I plug in a 0? Yeah, can I have 0 minus 9, square it, add 2? Mechanically, we can do those calculations, but the thing is that in this particular situation, there isn't anything over there. There isn't anything over there. Our inverse function doesn't exist to the left of x equals 9. There is nothing over there. We're not allowed to officially plug that in. We've got to make sure that we're aware of that. We don't want them to catch us off guard. We also don't want to have an incomplete or improper understanding of how all this stuff fits together. So let's come back to that idea of plugging stuff in and checking stuff out, because we've got that important relationship about how those inverses are interacting with one another. And this is very important, even though this is a very brief kind of comment to make. If we've got functions and we do the composition f of g and g of f, if we do those compositions and both of them spit back a generic x. So again, the idea, no matter what we start with, if we put it into g and then take that new number and put it into f, we get back the x that we started with. If we pick an x and put it in f first, and then take that new value and put it into g, do we get the x back that we started with? We've got to have both of those directions of composition working properly. If that happens, then we have inverse functions. So we could check this out. Part of what's going on, though, is this very specific connection that we kind of made a little bit of a stink about with our radical functions. Any of those even roots, we're only sticking with the positive version, so the positive square root. If we put things together, it's always the positive square root. So there's already this kind of restriction that's happening about how that stuff fits and works together. We don't want to accidentally overlook something like that. That's one of the helpful things about making that side note. And it has to do as well with the issue of evaluating. Because of all of these interactions, maybe instead of asking you to go through the process of finding the equation of the function, maybe they only want to ask you about what the graph looks like. So how does this stuff play out if we are instead worried about starting with the graph instead of the equation? Also sort of a four-step process here. We do a little drawing. We're going to draw our original graph. We're going to want to label it. That way we can tell our original function versus step 2. Flip the paper over and trace your axes and your graph. So we're flipping that piece of paper over, now looking at the back side and saying, maybe we need to hold it up to the light. Maybe we've got, a nice lighter colored desktop surface that we can just trace it through without an issue. We're going to trace through. We're going to trace exactly what we see showing through the paper. No label on that. No label on that one. We only labeled the original function. Now, once we've done that, so digitally we don't have to flip things over. Digitally, we don't have to worry about that. Digitally, we can actually do this third step and this and get the fourth step, and there we go. Third step has 2 manipulations that we're going to do. You've got one version where we describe things as flip that original drawing. So I'm looking at the original drawing, and I'm going to flip that upper left corner down to the lower right corner. And then I'm going to hold it there. So I'm going to take that upper left corner, I'm going to flip it down, I'm going to hold it there, and then I'm going to smooth out the piece of paper. I'm going to let that back flap out smooth, flap gets folded to the left. That drawing is the drawing of my inverse function. Now, if you don't like that version and instead you want to do this, here's a different description, and this is something that we can do digitally very nicely. We're going to start with that original drawing. So here's the drawing. It's labeled with f of x. I'm going to turn the paper clockwise 90 degrees. Then I'm going to flip the paper over top to bottom. So here's our drawing. We can take that drawing, we can turn it clockwise 90 degrees, right? Turn clockwise 90 degrees, and here's the picture that we get. Then we can say, okay, cool, I want to now flip that drawing top to bottom. So when we do that, and again, the digital version makes things nice to do, when we do that, we will get our inverse function drawing. Potato, potato, do whichever one you like best. If you started with a graph and needed to create the graph of the inverse function, these are your ways of being able to do that instead.